All right, so let's start with the lesson. So I hope you all open up now this lesson URL in your browsers, and we all scroll through it together. The title is Julia for High Performance Scientific Computing. The title derives from the topics here, which are so Julia, it's inherently a very high performance language, and it has been developed particularly for scientific applications, large numerical simulations, modeling, and so on. And this is here the outline. I will walk you through a motivation, what's special about Julia, why might you want to consider adding it to your repertoire of languages. And there are very rough timings here. I hope to be able to stick to it, but let's see how it goes. Let's just jump right into the motivation here. I will now change my screen a little bit to remove the left-hand bar. You can keep the bar there if you want. So motivation, why Julia? First, I want to actually read out to you explicitly verbatim a quote from the developers of Julia. It was developed originally at MIT some, I don't know, 10 years ago maybe. And this is what they wrote in a blog post. We want a language that's open source with a liberal license. We want the speed of C with the dynamism of Ruby. We want a language that's homoiconic with true macros like Lisp, but with obvious familiar mathematical notation like Matlab. We want something as usable for general programming as Python, as easy for statistics as R, as natural for string processing as Perl, as powerful for linear algebra as Matlab, as good at gluing programs together as the shell, something that is dirt simple to learn, yet keeps the most serious hackers happy. We want it interactive and we want it compiled. Did we mention it should be as fast as C? So this might sound like a complete utopia, a complete dream. This is not possible. But let's see what you think after attending this workshop. I think they might actually have realized this very high goal. So Julia really is fast. I'm sorry that the labels here are a little bit small, but this is a comparison of performance between different languages for a suite of micro benchmarks, so small kernels from typical scientific applications. So iteration, pi sum, matrix multiply, stuff like that. C is what you see here at the very left. It's the reference point. It's always, performance is always 1. And then you can see the other languages here. So there's a bit of spread, but Julia is really on par with C for this collection of micro benchmarks. You see Lua, Rust, Go, Fortran, and so on. And then at the very extreme here, Python, R, Octave, because these are not fast languages. They're not meant to be fast originally. They're meant to be dynamic. But Julia is really, it really is very fast. The two language problem. I actually have another task for you. I want to ask you this question. So have you ever written and prototyped code in a high-level language, I don't know, Python or R or Matlab, and then found it necessary to rewrite it or port it to a different language for performance? I will scroll down to the bottom of HackMD here, and I will ask you this question. It might be interesting to hear what you have to say about it. So scroll down to bottom of HackMD, and if you have a good question, a good answer to this question, please write it down. In the meantime, I will go back to the lesson here. I'm going to revisit, have a look at your answers in a minute. So to run code in any programming language, this is something you might all know, but it gives you a relevant background to what's special about Julia. So some translation into machine instructions or assembly code needs to take place. but exactly how the translation takes place differs between languages. So Python and R are interpreted languages. They translate instructions line by line, while C, C++, Fortran, and many other languages are translated to by the compiler before you run. So they're ahead of time compiled. And conventionally, there is a trade-off with programmer productivity being higher in the interpreted languages, which are considered to be higher level. You don't need to worry about memory management or types and stuff like that. So you optimize programmer productivity, but at the cost of much slower code. While the compiled languages are faster, typically by many orders of magnitude, but there's more, you need to write more code. You need to think about memory, you need to think about many things. So in many ways, Julia looks like one of these interpreted languages, and it mostly behaves like one. But before a function is executed, when you run a program, it will compile actually just in time. So the Julia has a compiler, and just as you execute code, it gets compiled on the fly and then executed with very high speed. So we will come back to this later because it's one of the main key ideas here behind Julia. Another selling point, if you will, of Julia is the composability. So what is composability? It's in the case of Julia and programming in general, it means that you can write generic code, just typical code. You can write code in modules and packages, and they can be completely independently developed, but you can simply use them together and they work as you would hope them to work together. So just to concretize this, I will show you a very cool example, which is, it's well known. It's sometimes discussed in when you talk about composability. There is this interaction between actually three packages. So differential equations is a very large, very powerful package to work with differential equations in Julia. Measurements is a package for working with numbers that have uncertainty, some statistical uncertainty, so error bars. And there's the third package, which is plots.jl, which is for plotting. So here's code that solves this simple pendulum equation. You import these three packages, differential equations, measurements, plots. And this is something that becomes possible with a measurements package. You can specify here the gravitational constant plus minus, so 9.79 plus minus some error bar. And many other numbers are defined here with error bars. Okay, so that's the measurements package. Then you define a function, which is your simple pendulum. And then you solve it using stuff from differential equations. So you define some ordinary differential equation problem, and then you solve it. And then finally you plot it. So all these three packages have been developed independently to solve different problems, but they simply compose perfectly together. So when you do this, you get a result with the error bars. So this is pretty cool. You don't need to think about anything here. So the functionality just translates between these packages. Okay, I want to go back to HackMD. Yeah. So implementation in Octave, rewritten in C++. From Matlab, Matlab was too slow. I had to rewrite everything in Fortran. Python to NumPy, yeah, that's not a big jump, but it still requires some effort. Matlab to C's CUDA. Yeah, so this is, so the two language problem, I didn't really dwell on it that much. I'll go back. The two language problem is basically when you combine, you prototype code in Python or R, but then you want to run your simulations, you want to publish papers, and it's too slow. You want to run it on a cluster, and it simply won't work. Your prototype is too slow, so you have to rewrite it. You have to profile to find, maybe rewrite certain parts of your code. With Julia, this problem vanishes because your prototype code is fast from the beginning. So thank you for your answers. This is interesting. There's a question, is there a way to define compile time constants? So there is an expression in Julia. I don't think I talk about it much later. So you can define consts, a const variable equal to something. It actually doesn't mean the same thing as in C++ or other languages. It doesn't mean that the value never changes. It means that the type will never change. I can come back to this question later. Okay, back to the motivation. So when not to use Julia, it's not a perfect language for everything. So time to first plot is sometimes discussed, TTFP. So because of this just-in-time compilation, if you're using a package like plots, for example, to plot data, when you load it the first time, it actually takes a few seconds because it's pre-compiling lots of functions and stuff. And that's why Julia is not appropriate if you need to plot 1,000 figures and you want to do it with a script that gets executed 1,000 times. So that's going to be very slow, but there are workarounds. Use a long-running REPL, so read, evaluate, print loop. So when you have the Julia session open, or you can actually pre-compile to an executable. The ecosystem of Julia is still less mature than, for example, Python and R. So you might not find a package that corresponds exactly with your, a package that you're already using in a different language. The good news is that it's straightforward to use external libraries in Julia. You can call Python, you can call R, and you can call C and Fortran as well. And you can actually write fast Julia code with not a lot of effort compared to many other languages. So you might write your own version. Rapid package evolution. So it's still a fast-moving language. Many of the major packages are stable now, but there are many packages that go through large changes often, which can break your code, which is, of course, very annoying. But the good news maybe is that Julia comes with a very powerful package manager, which we'll look into, which has inbuilt support for isolated environments, software environments. So you can specify all the dependencies and you can make a reproducible environment that can be run on other machines and nothing breaks. Large memory footprint, because of the pre-compilation, there's a large memory usage at runtime. This is still, there's no direct workaround, but there are future plans to enable building more lightweight runtimes in future versions of Julia. Okay, so what you will learn, I've told you roughly, we'll talk about HPC, we'll talk about writing efficient code, multi-threading, multiprocessing, GPUs. Today we'll focus on developing in Julia, writing tests, working with data, visualization, and some simple machine learning. But I also want to emphasize what we will not learn. So we will only be scratching the surface. It's a short workshop, 2 half days. So we'll just be scratching the surface, but every part, every section of the material has some recommended additional reading, which you can go through later. I will not go into interoperating with other languages. I mentioned that it was possible. So you can call Python, R, C, Fortran, relatively straightforward, but it's outside the current scope. I'll not directly talk about using MPI with Julia. We'll talk about parallelization in more native Julia ways. It's totally possible to write MPI code with Julia, but again, it's outside the scope because if you know MPI from a different language, you also know how to do it in Julia. And then, there are many great packages for different domains of scientific computing, physics, chemistry, biology, and so on. Will not, of course, go into any details there because you all come from different backgrounds, but you can get an overview later of some of the major existing packages. Okay, so that was for the motivation. So it's 9:30. I'll go back to this question later. Are there any immediate questions now? If not, I'll just go ahead. After the next section, we'll take a break. I didn't mention that we will, I will try to take frequent breaks so we can all refresh our minds and keep focused. So I'll press the next button here at the very bottom of the page. This takes us to the overview. I actually have to move the sidebar manually. So what are the special features of Julia that perhaps set it apart from other languages? Specifically, I'll talk about the type system in Julia, how a language can be both dynamically and statically typed. What is this multiple dispatch paradigm? This is one of the key design principles of Julia. You'll learn what it is, how it works. Code introspection, what is that? What is metaprogramming? So these are some of the things that are maybe a little bit different from what you might be used to. So I mentioned that Julia is a dynamically typed language. It does not require you to write down any types. You can just write a equals to 1.0 or something, and that becomes a float. But maybe counterintuitively, it's nonetheless because of the sophisticated type system in Julia that it becomes very high performance. And this is because the types are inferred by the compiler and code is specialized. I'll come back to this. So it's good to have a mental model of types in Julia. I'll just start by mentioning that there are abstract types that define a kind of a thing, sets of related types, and concrete types. So to start exploring this, let's all now start up Julia. So if you haven't already, please open up your Julia REPL. So I accomplished this by typing Julia in my command terminal.
Excuse me.
Yeah.
Julia notebook, would that work too?
Yes, that would work. Yeah. So after an hour, we will actually switch to using VS Code. But I wanted to start in the REPL. If you want to use a notebook, that's fine. You can open up the notebook too. You might, yeah, I can try to point out what will be the differences. So I'll just give everyone a minute to start up Julia. So it might be maybe on some operating systems better if you click a Julia icon in your application list of applications, and that should open Julia. So what I mean by opening Julia is that you get something like this. I'll increase the size a little bit. Okay, so if there are any problems, please let us know. You can write down in HackMD or you can speak up. I hope you all have Julia installed and you're able to open up this so-called REPL here, REPL, the Julia, open up a Julia session. Any problems? Okay. So what do we see? We see this prompt. It says, Julia, we can start writing. It tells us that we can type question mark for help. We can type this right square bracket and then question mark to get help with a package manager. So we'll come back to this later. I'll move my terminal here and scroll in the background. So we can start writing code. We can do a is equal to 1. I wanted to tell you about types. So let's look at the first inbuilt command here, type of. You can type along or you can watch, it doesn't matter. You'll get lots of experience typing yourself throughout this workshop. So type of 1, it's an int 64. So Julia knows the type of this. I can do type of 1.0, it's a float. There's inbuilt support for complex numbers with IM. So this becomes a complex float 64 type. And I maybe mentioned, I don't remember, that there's the type system in Julia is hierarchical. So all the types are arranged in a hierarchy. And I can pick one of these types, float 64, for example, and look at all the super types. So the super types of float are abstract float, real number, any. Any is at the very top of the type tree. And then I can look at subtypes of, for example, real. Real is one of the super types of float. So the subtypes are abstract float, abstract irrational, integer, rational, and so on. So here you see a representation of the type tree. This is only for numbers. There are other hierarchies for arrays and so on. So there's a wide variety of possible types. I want to tell you about derived types because they are very important. It's very common when you write Julia to define new types that fit particularly well for your particular problem. And this is encouraged in the language. They're not slow, they're fast if you write your own types. I will sometimes be typing out code and sometimes I will be copy pasting. You can do the same. To copy paste, you can simply block the code like this, or you can also press this little button. You can press this button here in the top right corner of the code cells. So here's a code cell. I can just press the copy button, move back to my Julia REPL and paste it like this. So I can now define, I just created a new custom type. I can do p is equal to point 2d, and then I call it with some arguments, something for x and y, and I have a new type. I can access the elements with p.x, p.y. This is completely without any types. You see here, there are no types here, but what's actually quite common to do with these structs, so the keyword is struct, it's to use a parametric type. So you see there's angular bracket t, and then x and y get the type t. You could also pass two different types if you want, t and t1 and t2, or t and s. So if I do it like this, I can define 2 points. t1 is equal to 0.12. You see now that this particular variable becomes a point with int 64s. Do this with floating point values, I get a float 64 point. And this defines a new type hierarchy. So point int 64 will be a subtype of point. So point will be a supertype. So this symbol here means, is this a subtype of? So point int 64 is a subtype of point. That's true. There is a sneaky reason why I call this here a 2D point, and this just I call point. And that's because many things can be redefined. You can redefine functions, variables, and everything. Structs cannot be redefined. So if I wanted to call this point 2D, it's an error. It's an invalid redefinition of a constant. point2d. So you would need to restart your REPL in order to redefine a struct. But other things are redefined. So it's very common to work interactively like this in the REPL. That's why I thought it would be useful for us to use the REPL in the beginning and to work interactively in VS Code, as we'll do later today. But some things cannot be redefined. So yeah, I wanted to tell you just how you might be coming from Python or other languages which are object-oriented. Julia is not really object-oriented in the same way. You can write, it's a multi-paradigm language. You can write code in many different ways, but sort of the canonical way is to structure your code around types. So you specify types, you define types, abstract types, and hierarchies of types, and then you define functions that operate on the types. So this is fundamentally different from object orientation, where you write the classes and the functions of the classes belong to the objects of the classes, right? So you define objects and those objects have functions. It's the opposite way, really. In Julia, you define the types and then you have functions for particular types of types. And here's just an example how you might want to structure code around some concepts. So if you're describing animals, you might want to describe an abstract type called abstract animal, which sits at the very top of the hierarchy. You might want to define an abstract dog being a subclass of abstract animal. Same thing with abstract cat. And then you might want to define this a type, a struct, dog, which is a subtype of abstract dog and has these. So this is a concrete type now, right? These are abstract, this is concrete. The concrete ones can hold fields. So the dog type can have a name field and a friendly field, which is a Boolean. While the cat, it's a subtype of abstract cat. It has two different fields, so name and hunts mice. Okay, that's nice, but why would you want to do it like this? Well, then you go ahead and define methods or define functions. So you might want a function called getName, which will be common to all the subtypes of abstract animal. So you simply define it for the abstract animal. So here you specify the type explicitly with a double colon here. And this function will work on all the types that are subtypes of abstract animal. You might want to define a different function only for the abstract cats. So it'll work on all the subtypes of abstract cat. And you might want to define a new instance of a cat, and maybe I'll just, yeah, you get the idea. You call functions for functions that are defined for particular types of types. So this is not object orientation. It's slightly different, but if you really like object orientation, there are resources, particularly at the bottom of this page, which might be useful for you if you want to structure your code in an object-oriented fashion. Are there any questions on this? Does revise allow you to redefine structs? The answer is no. So I'll talk about revise shortly. Functions and methods. This is how you define a function. Sum square with two arguments, x and y. Again, there is no need to define any types here. Let me copy paste this. I can now actually if it's a short function like this, it can sometimes be more elegant and short to write it on a single line. So this reminds really of how you would write it down mathematically. So you don't need the function and end keywords if it's a short function. You can write it on one line. So what happens now? I define a function without any type specifications. If I call it with integers, I get an integer. If I call it with floats, I get a float. I could call it with complex numbers or whatever. I just wanted to mention here that we specified the function without any types. In most cases, that's a good idea to write general code without specific types. But there are reasons for adding the types. One of them being simply to improve readability. It's good to know what types a particular function is meant to handle, to catch errors, and specifically to take advantage of multiple dispatch. And this is the idea, is to implement different methods to the same function. And to make that, maybe it sounds strange, to make it more concrete, let's just do this exercise together here. We have this function, sum square. It's a generic function with one method. We can add a method to sum square. And that's indeed what we often do. So we define this this particular type called point, which had two fields, x and y. Let's say we want a sum square function that accepts points, 2 points. And we can decide that we want to take summed squares of 2 points. And let's say we define it to be this. So the summed square of 2 points is, p1x squared plus p2x squared, p1y squared, p2y squared. So let's write a new function sum square, p1 of type point, p2 of type point. And we want to return a new point. And maybe this is a little bit arbitrary, but let's say this mathematics looks like this, plus p2x squared. And then for the y, we have p1y squared plus p2y squared. And press enter. It's exactly the same function name. Sum square is now a generic function with two methods. So the same function has two independent methods which work on different types. What we can do now is to write 2 points. P2 is equal to that's the point. And we can call sum square of P1, P2. And it returns the right thing. If we call it again with just the integer inputs, we get a different answer, right? So you see what's going on here. To see all the different methods that have been implemented for this particular generic function sum square, I can use the methods function. So I take the methods function and pass sum square into it. So this is actually an example of where I'm passing a function into a different function. And it tells me now that there are two methods defined for this generic function sum square. There's the one we just defined with points, and there's the other one that we defined in the beginning. So I want to emphasize that a function describes the what something is doing. But it can have multiple methods describing the how. So that's often how you structure your code. This differs again from object-oriented languages, where it's the objects that have methods. And what is this multiple dispatch? I promised to tell you about that. So it's when Julia at runtime selects the most specialized method to run based on the types of all the input arguments. So importantly, it's called multiple because it takes all the input arguments and dispatches the right method for the types of input arguments. So the best practice here is to constrain argument types to the widest possible level and introduce constraints only if you know that other argument types will fail. And this results in fast code. So it's maximum generality, and it has good performance. I'm running a little bit behind on time. I'm slower than I hoped, but let me talk about type stability. I'll tell you about this briefly, and then there is an exercise. There's one thing you have to watch out for. This is a so-called type unstable function. Why is it unstable? It's a function that receives an argument. If the argument is smaller than 0, it returns 0. If it's larger than 0, it returns x. This is actually like the ReLU function in machine learning. If I call this with 1, it gives me a 1. If I call it with a -1, it returns 0. That's not problematic. If I call it with 1 plus 0, it gives me 1.0. If I call it with -1.0, I get 0. So this is an integer. This is a float. So when you have something like this, Julia, the compiler, will not be able to, it will not know at runtime what types the function will be returning. So it will not be able to generate fast code. So this is type instability. And this is something one needs to watch out for in Julia. A standard way to solve this problem is to use various types of inbuilt functions. So here is a type stable version of the same function. So instead of returning 0, I return, so this function 0 parenthesis x, which, what is this? It's, I call it with a float, I get a floating point 0. If I call it with an integer, I get a integer 0. So that's the idea. Okay, compilation. I just want to give you a brief idea about what happens. So I told you about interpreted languages, compiled languages, and then the middle ground occupied by Julia, which is just-in-time compilation. So this is what happens when you execute code. It takes the source code, it parses it, it abstracts the syntax into a so-called abstract syntax tree. It generates code with a compiler. This is not target specific, depends on which machine you are on, which operating system and so on. It creates some so-called intermediate representation, LLVM. It creates, I'm not an expert, so the backend LLVM, I'm not sure exactly what the difference is. And finally, it results in machine code, which gets executed on the machine. And sometimes there is this loop here. If it turns out that something needs to be recompiled, that can happen. It goes back here, generates code, and keeps running. You can actually look at all these lowered forms of code with these code introspection macros. So I think this is pretty unique among programming languages. So Julia is aware of itself. It can, you can inspect the code it generates. There's code underscore LLVM, there's code underscore native, and so on and so on. This starts to look more like assembly here. And many of them are not generally useful when you write code, but this particular one is useful to warn us about types, type instability. So you get information about all the types that the compiler has deduced. So we didn't specify any types for the sum square function, right? But the compiler knows the types. It knows what's happening here. Meta programming, just gonna briefly show you how that works. It's when you write code that writes code. So this is something which derives from Lisp. So there's inspiration in Lisp and Julia still today. And I just want to show you, this is what the compiler actually does. It parses source code. X plus Y is a statement. It parses it and creates this abstract syntax tree. This is a part of the abstract syntax tree. You have a head sort of symbol, and then 3 symbols that derive from the head symbol. You have plus, and you have X, and you have Y. So this is like an abstraction of the syntax. This probably sounds weird to some of you, but I just want to get to the bottom line here, is that because this abstract syntax tree gets generated, you can also modify it with code. You can modify the abstract syntax tree with your own code. And here is an example of a so-called macro, which does this. So Julia has many macros. You can write your own macros. A macro is sort of like a function, except you use the macro keyword here. And what this does is to accept 2 arguments, some number n and some expression, some code. And what it does is to write a for loop from 1 to up to this number. There's some special syntax here, quote and escape, ESC, and so on. I won't go into those details. I just want to show you that this is possible. We can define a new macro called do times, and then we can call it with an @ symbol in front. I can do something 4 times. I can do println hello, like so, and it creates it does this 4 times. So this is automatic code generation. When you use this macro, it actually inserts a for loop into the abstract syntax tree. If there's a macro you want to use, you want to inspect what it's doing under the hood, you can use this macro expand macro. So macro expand, and then I write the macro together with some input, and you can see that, yes, indeed, a for loop was inserted here. Finally, so soon it's time for a break. I just want to mention that there's full Unicode support in Julia. You can write Unicode symbols. You can write smileys if you want. Sometimes this is used. Greek letters are common. You can use, actually some of the Unicode characters have a meaning. So you can use the square root symbol. How do you do that actually? It would be annoying if you just needed to copy paste, but what you could do, what you can do, and what people do is to use this LaTeX syntax. So for the square root character, you type \sqrt tab. You can type 4. This actually has meaning. But you can also define a variable sigma is equal to 0.01. And then you use sigma like any other character. All right. So it's 5 minutes past 10. There are just some relatively short exercises here. So I suggest that we work on these exercises for just 5 or 10 minutes, and then we take a 10-minute break after that. So let's have exercises until 10 minutes past 10. I'm not going to split up into breakout rooms because these are relatively short. Let's keep everyone in the main room. Just play around in the REPL. You don't need to do these particular exercises. If you haven't done it before, you can also just get familiar with a Julia REPL. But if you want to, you can have a look at these exercises here. They have solutions. So at 10 minutes past 10 Central European time, we have a break for 10 minutes. Don't hesitate to complain if there is some problem, if I'm not heard well, if the font size is too small. I can always zoom in on the page here, or let me know. It's time for the third part, developing in Julia. So what development tools exist for Julia? How can I write modules and packages in Julia? How do these environments work that I mentioned before? How can you create a reproducible environment? How do we write tests, unit tests? Tooling. So we will now switch from the Julia REPL to Visual Studio Code, VS Code. So this, I'm not sure, some of you are probably already using it, or many of you probably aren't. It's developed by Microsoft. It's open source now though, Visual Studio Code. It has a very powerful Julia extension, and it has become the favored development environment for Julia, because most efforts have, there have been other editors like Juno, part of Atom, but people developing in the Juno extensions have now switched to VS Code. But there are alternatives. Someone was already typing in Jupyter earlier. Many people use Jupyter notebooks. So in case you didn't know, JU in Jupyter stands for Julia. It was already thought of as one of the languages for Jupyter notebooks. Pluto is a Julia version of Jupyter notebooks in a way. So it's the same idea. You have notebooks, but they work slightly differently. I think they claim to have solved one of the problems with Jupyter, which is this possible confusion with out of order execution of code cells. You know, you can run the code cells in any order, and then you might introduce bugs if you run them in not in a linear way. So in Pluto, they are the notebooks are reactive. So whenever you execute a code cell, all the other code cells that get affected by that cell get re-executed, I think. But I actually haven't used Pluto myself. Some people still prefer other text editors, Nano, Emacs, VI, Vim, followed by running code with just Julia and then your file name. And there are some plugins for these Emacs, VI for Julia. Again, I don't know those, but one can Google, one can search on the internet, Emacs Julia, Vim Julia to find out more. Okay, so using VS Code, I hope you all have it installed. Let's now open it up. So either you go through a file browser, you click on the application symbol, or I'm not sure if this always works. It could be operating system dependent, but on my Mac, for example, I can run code, this command in a terminal, and it opens up VS Code. Okay, so all of you open up VS Code and move it to a convenient location on your screen. I will now have VS Code open in half screen like this. So you could put your VS Code window on the other side, something like that. I hope the screen logistics, the screen real estate space can be organized in some way for you. I know it can be a lot with online workshops. You have all these windows open. We have HackMD, we have the lesson, but let's see if it works for you. You should see something like this. It's a get started page. I'm gonna press this open button here to open a directory. That's most convenient. Open. I will go down to my Julia folder. I will create a new folder here. So I would suggest that you do something similar. You can create a new directory called Julia, or you can put it on your desktop if you want. I'm going to create a new folder called workshop. I create it. And I want to work in this folder. So I just press the open button here. It's an empty folder. What shall we do? We should open a new file now. So one can actually create Jupyter notebooks directly or a text file. So I'll just create a text file and I will save it. So you should be typing along. Hopefully I can give you some time to catch up if it's difficult to multitask right now. I want to save it. I can do save as. For me, there's a keyboard shortcut here. Command Shift S to save it as, let's just call it hello.jl. And let's just do print ln hello Julia. So if you are new to VS Code, maybe I should just tell you that there are these tabs here now. I can get rid of this get started page. I'll just close that one. One can have multiple tabs. One can have a terminal open below. On the left, we have different menus. This is where you install the extension for Julia or other extensions. I'm just going to collapse this left menu to get more space. So on my machine, it's Command B. It could be Control B on Windows and Linux, like so. Okay, I have a Julia script, a simple program. I could go here up to the play button, execute active file in REPL. There's some other ways to do it. If I go here, execute active file in REPL. Yeah, what we could do is one thing I should teach you right away. So if you press Control Shift P or Command Shift P on Mac, what you get is this quick search. So there are many different things you can select here. You see, it's a huge list for different languages, debugging, this and that. You could start a Julia REPL. You could also type execute active file in the REPL. There are many ways to execute the code. That's what I want to tell you. But this Command Shift P or the Control Shift P to bring up the help is super useful. So I would suggest you get used to it and memorize the keyboard shortcut. What I want to do is to execute this in the Jupyter way. So I just hit Shift Enter. This should be operating system independent. Shift Enter, what happens? Something happens at the bottom of the screen. Something is loading. A Julia session is loading. Takes a while, yep. And now it actually executed this, this code. Okay. So that's mission accomplished. Just to get started, there's a link here, documentation for the Julia VS Code extension. It can be useful. So this section here is all about developing in Julia. I want to tell you about modules and packages. So let's write our first module. First, I want to tell you about module scope or scoping in Julia generally. So normally code is encapsulated in modules in Julia. You can write free scripts just in one file like we're started doing here. But whenever you're writing more elaborate code, usually one puts it into a module. And then there are different ways to use modules. You can use the using module name or the import module name. The difference is that if you use using, all the exported names from the module, so these can be variables, functions, macros, they are brought into scope. So you can just type them directly. If you use import, the difference is that you need to qualify the names. So you would need to do module name dot function for some function here, or module name dot variable. So let's just copy paste this module here. Let's create a new file. I could go to file, new file. I just paste in, and VS Code is clever. It detects that this is now Julia syntax, so syntax highlights it, and I will now save it as points.jl. So again, you should be typing along. this is what we worked on in the previous episode. So the point struct and the sum square function. And when I mentioned all the exported names, this is what I meant. So we create a module and we select what we want to export. So everything will be available from the outside, even the non-exported names, if you qualify the name, if you write points.point or points.sum square. But the exported names will become added to the namespace when you import the module directly. I can execute this. Okay, it got evaluated here in the main scope. So let's now try and import and use this module. We could either include a particular file with include function, or just what I did, shift enter to evaluate the whole file. And because this module, this is not standard when you're when you have downloaded packages from the internet and you're going to use it. This is not what you need to do. But this is what we do now because we define the module in a new function locally. And because we saw here that the module was defined in the main scope, what we actually need to do when we use the module is to use this using dot notation. So dot because points is defined in the current scope. Let's try that. Hope it works. Yep. Now we can use everything from the module points. We could define these 2 point types, call the function, and it'll just work. I could execute it here in the REPL. Let me just resize the window a little bit so this does not, is this visible even the very bottom of the VS Code editor?
Yes. Yeah.
Okay, everything has just worked. I want to bring your attention to this function names. What I could do is to write names and then the name of the module, and it tells me exactly what has been exported from this module. So this is the name of the module. There's the struct, the custom type point, and the function sum square. And these are exported here as symbols with a colon in front. Okay, we're just starting starting small, and then we'll start building up. There was a question in HackMD earlier about revise. This is a very good package, very important actually. So before it was developed and added to the Julia ecosystem, it was necessary to restart the Julia REPL whenever one was developing a package for the new changes to take effect in the REPL. So this is, of course, an obstacle when you're developing code. You don't want to be reopening a new REPL all the time. And that was because of pre-compilation. When you do using some package, it just in time compiles that package. But this is not needed anymore when revise is loaded, because revise tracks the changes to the modules that you're developing, finds out what has been modified, and recompiles only that. This is something we don't need to worry about much in VS Code because it's loaded by default. But it's important for you to know about if you're developing code differently, not in VS Code. You should install revise. I will tell you how to install packages in a minute, and then you should use the revise module before you import your package that you're developing. Okay. Again, please interrupt if there are any questions. No questions in HackMD. Let's have a look at the package to see the structure. So I will open up this example package in a new browser tab. This is just a very minimal package that is shipped with Julia. I just want to show you the structure. So there's a docs folder with documentation, source, and test. license. So most packages in Julia are open source. If we go under source here, this particular package has only one module file. Normally, you have many more files, which are organized by functionality, but you always have this one file with the same name as the module itself, as the package itself. And there you have this high-level description, or you define the API of your package. So it's a module, you define what you want to export, and maybe you include source files that are here in the source directory with include function. Because this is a very small package, the functions are defined here in the main module directly. Okay, that was the source folder. There's a test folder with tests. And there's always one master script, run tests.jl, which define your scripts. They could be including, again, other test files, but because this is a small package, everything is done in this run script.jl. I will tell you how to write unit tests later. So this is an example. We're testing the hello function. We're testing the do math function. Finally, I want to tell you about the project.toml file. What is this? This is like in Python conda.yml or the requirements.txt file, or the environment.yml file. And there's probably something similar in R that I don't know about. So this is the project.toml file is a high-level description of some metadata, version, name, a unique identifier, compatibility. This is for Julia 1 and later, extras, and targets. There are no dependencies. There could be another section called deps, which includes all the packages that this package depends on. I will come back to project.toml and manifest.toml, which is another file, in a minute. All right, so this was the high-level overview. The package manager, I promised to show you because it's very powerful. If I go back to the VS Code window, to enter the package manager, you type close square bracket. So this character here. If you do that, you see that it changes. Your prompt changes. It shows a version, an environment actually here, and it shows package. I could type help. It shows which keywords are defined. For example, add. This is how we add packages. We can build, we can garbage collect, we can generate a new package, a new project, and so on. We can remove a package. Remove. But I just want to draw your attention to this, that we will use a different, so the lesser material has a different convention so that you can still copy paste things into your Julia sessions, because you cannot easily copy paste this particular character here. So this is another way to use the package manager. You import it with using pkg. And then, for example, to add a package, you use pkg.add the name of the package. And then there's status. If I do status here in the package manager, what does it show? It shows these are the packages in my root environment. This is the root environment that I currently have. Okay. So installing and using a package. Let's install this example.jl file package using the package manager. So you can copy paste from here, but I will just do it the package manager, this in the particular package manager mode by typing add example. Okay, it installed something. actually, sorry, I already had it installed. I forgot to uninstall it. You will probably see a new package in your default root environment. You should see that example version 053 has been installed. After installing it, we can use it. So I could go back, I press backspace to get back to the normal Julia prompt. I could type using example, and then I can call this function do math, which is defined. And what was it called? Hello world. Yep. All right. So we just installed a new package in the root environment or the default environment. We can see that from here. It's good practice to use isolated software environments. This is the same as in Python and probably R, to avoid dependency clashes and to also ensure reproducibility. So let's create a new environment and install packages there instead. This is again type along. If you have time, you can type as I type, and if you fall behind, you can catch up later. So let's go back to the editor. I'll just move this up a little bit, I think. So what did I want to do? I want to do first, many of these Unix commands for navigating the file system are actually defined in base Julia as functions. So I could type pwd parenthesis, call that function to see where I am. And what do I want to do? I want to create a new project, a new directory. I want to change directory, go into it, and then activate it with the package activate command. Let me just copy paste. I have an imported package. I have to do using pkg first. Okay, it activated a new project in this directory here that I just created. And we can see if I go to the package manager now with closing square bracket character, that we're in a new environment. If I do status, it's an empty project. An example once more. It was very quick because it actually reuses existing installations from the default environment when they're available. So if I do status, I see I just added example to the new environment. This will now work only on Mac and Linux, I think. So if I type semicolon character, I get a shell environment. So here I have access to all Unix commands. Unfortunately, this does not work, I think, out of the box on Windows. I think maybe you could try still on Windows and type dir or something like that. But I can use ls, for example, and I see the project file here now. It's a configuration thing in Windows. I think it depends on your, you can configure this. Unfortunately, I don't know exactly. You can configure this to work with PowerShell or something like that.
Yeah.
But it's something that needs to be configured. I just wanted to draw your attention to that a new project TOML file got created with example here in the depths field, depths section of the file. There's also a manifest file. What's that? It has more information. It tells us exactly the version of example and so on. And I just summarize project.toml and manifest.toml here. So the project file describes the project on a higher level, including what package dependencies and compatibilities there are, and some metadata. The manifest file is an absolute record of the state of all the packages in an environment. And this file can be used if you want to create an identical environment on a different computer. So that's for reproducibility. And manifest normally should not be edited by hand, but the project file can be edited by you. I want to also draw your attention to another possibly confusing aspect of environments. So project environments inherit from default environments. So if I have a package installed in my default environment, and then I create a new environment, I still have access to everything available in the default environment. So one simply has to be careful to add all the needed packages to a project environment that you're working on. But I think it's intentional. So the benefit of this is that some packages like revise, test, benchmark tools that we'll talk about later, they can be installed in the default environment rather than project environments to avoid cluttering. So that's a gotcha. Creating environments for other projects. If you are if you receive a project from someone else and you want to recreate the exact environment that the other person has, you clone a package or you download a package somehow, and it will ship with the project file and or the manifest file. And if you install using the project file, all the dependencies will be installed, but not necessarily with the exact same versions. But if you use the manifest file, you will get the same state of all the packages. And this is what you do. You first activate the environment. If you do activate dot, it will read either project.toml, or if the manifest file exists, it will read from that one. And then you do an instantiate call to download all the packages in the right versions. Okay, so generating a new project. So a project, also known as a package. Maybe you want to create one yourself for your own code. What do? We use the generate command. I will now check where I am, pwd. I don't want to be here. I want to do so what was the command again? Change directory. I forgot what it was. How do I change directories? Oh, cd, of course. I just do cd, and then this will work on all operating systems, I think. pwd, I just changed directory. I want to be here because I will create a new project using the generate command. I can do this in the package manager mode by typing generate package. It created a new directory and it created files. It created the project file and it created the main module file. I can cd into my package. And then I want to activate the current environment. Where am I? I'm still in this example project environment. But I wanted to activate the new environment. Activate, oops. Let's go to package mode. Activate. First, I'll tell you one thing. If I just type activate enter, that's the same as deactivating, basically. So I go back to the basic environment, the default environment. Now I want to do activate dot. This is the new environment called package, my package. And now I can, for example, add some dependencies here, add example. I will not do the rest. There is an exercise for you to create your own package at the end of this. So I just first want to tell you about testing. I'm just going to save a little bit of time here and just tell you about testing, and then you can implement it later in an exercise. So we saw something like this in the example package. This is the name of the testing package. So it's called tests. You do using tests. And then you use these macros. For example, this is one macro, @tests. And then you have, this is sort of like an assert. Check that these are identical, that you get on hello Julia if you call this function. If you want to compare numbers, so numerics, you usually want to take into account numerical inaccuracies, so floating point, limitations of the floating point numbers simply. So two numbers are rarely identical, but what you can do is to use the approx symbol. So approximately, approx, I type tab again, I get approximately equal to. Usually you do more tests than only one or two, and typically you would organize your tests into these test sets. So you can define a new test set block, test set, some name, testing the do math function, begin, and then you run multiple different tests, one for a float, one for an integer, one for a complex. Sometimes you want to test that you get that something crashes. For example, calling this do math function with a string, it will not work, and it should give us a method error. And you can make sure that it actually happens, that it gives you a method error. Okay, so the test package gives you access to these very useful macros that you can write all your tests in. Some packages maybe want more advanced functionality, and there are other packages that one can look into if you need something more. But let's do the exercises. There are two exercises, three. You can start with the first one because this prepares for the next section that we will go through after the exercises and after the break. So please create a new environment using what you just saw and install data frames, polymer penguins, plots, stats plots, flux, and MLJ. And a suggestion is that you open this or run this in a new VS Code window, file, new window, because it will take time, especially Flux here. It's the machine learning in Julia. It's a big package. And you don't want your, it's good if you have the currently open window available for the other exercises here. So create a package out of the points module. There are solutions. Write a test for the sum square function. So let's say, shall we say 10 minutes and then 10-minute break. Maybe the exercise should be 15 minutes. Let's, between 10 and 15 minutes. So let's just say 11:15. And then we have a 5-minute break after that. So at 11:20, maybe a little bit later, we come back to the main room. We are now ready for the last part today, which is an overview of scientific computing. It's a bit vague. What I mean is the ecosystem of libraries that are available and that you might be interested in looking at. And then, because data science is on the rise, people from different disciplines work with data, I thought I could introduce you to a workflow, plotting, loading data, analyzing data, and doing some machine learning, just because it's popular and people work on those types of problems across different disciplines. So first I want to give you an overview of different libraries, different organizations that exist for collecting packages for different disciplines. And then we'll start with some data science, loading a data set, analyzing it using machine learning libraries. So I mentioned earlier that the ecosystem of libraries is more immature in Julia compared to Python and R. But that doesn't mean that there is not already a lot out there. So here's an overview. Hopefully this can be of some use to navigate if you are looking for particular functionality. So it's grouped here into mathematics, different natural science domains and data sciences, machine learning and stuff like that, statistics. So these are high-level organizations. So if I click one of the links, Julia Diff. So people in the Julia community, they get together, they are developing independent packages, which maybe are related, they have a common theme, and people get together and create these organizations. So Julia Diff is a collection of different packages for differentiation. And same thing for, I don't know, BioJulia, genome graphs, biosequences, and so on. There's quantum computing, there's finance, Julia Quant, signal processing, astronomy, physics. Anything that anyone would particularly want to discuss? Of course, I don't know much about any of these packages. I'll move on. Working with data. So we'll explore a Julian approach to a common use case, loading data, working with data, visualizing, and machine learning. So Julia is a good language really to use for data science problems. For one, it's because of the two language problem. You don't need to write first prototype code in Python or R or Matlab, and then call some library in a different language for some heavy lifting. So the two language problem is solved by Julia in this case. So let's start by downloading a data set. And this is a fun data set. It's a data set with penguins. There are 3 different species: chinstrap, Gentoo, and Adelie. Hopefully you all added this package in the previous exercise. We can import it using Polymer penguins. I switch back to my VS Code. I already installed the packages here. And as you can see, I am in a data science environment now. Where am I? I'm in the data science folder. Let me create a new file. And let's import data frames. I want to save this file as, I don't know, datascience.jl. And I want to save it in the right, I want to save it here. And then I import data frames. And I also want to import Polymer penguins. So there is soon a type along session. You can type along now, but I'll get to a formal type along session in a minute. So what are data frames? You might be familiar with the corresponding packages in Python or R. Dataframes.jl is the Julia version. So it's a library to work with tabular data, organizing any types of observations, any types of data. You can create a new data frame by creating 2 lists here, for example. Oh, interesting. I have a clash. I have a name clash. I thought I tested this. So cannot assign a value to variable base names. Base names already exists. What is base names? It's a function. My bad. So I cannot call this variable names because it clashes with the base.names function for the answer. So I'll just change this variable name to first names. First names. And we get this nice looking tabular representation of our data. Okay, so now is type along. So let's create a new data frame containing the Polymer penguins dataset. So in this code cell here, we use the Polymer penguins.load it defines a new variable, which is of type CSV file. And in the background, Polymer Penguins uses the csv.jl package for loading data fast. If you're not working on a data set which is available in a module, it makes sense to use the csv.jl package for loading data, writing data to disk. Remove this initial test, and I will load the data set with table the Polymer Penguins.load. I think it takes a little bit of time initially because it's fetching it from the internet. And I'll create a data frame with the table object here. See, it's I think I. Oh, everything's fine. It just takes a little bit of time. I can just scroll down here in the meantime. So if you're familiar with pandas in Python or the data frames library in R, this might look familiar. You can slice data frames. You can slice with a stride. You can refer to column names either with their symbols. So everything that is starts with a colon, it's a symbol. Or you can use a string version of the column name. You can use dot notation just like you can with pandas. So to print the species column, you can use a list of different columns here. And here's a little detail. So you can get access to all the rows. So this is row column order, either with a colon character or with bang, so exclamation mark. And the difference is that with exclamation mark, we access the columns directly without copying. So it's like a view into the data frame rather than a copy. If you need to save memory, you would want to use exclamation mark. We get size, number of columns, number of rows of a data frame with these functions here. And if you want, for example, to find unique entries in the data frame of a particular column, you can use unique here. So here's our data frame now. I will just increase the size of the window for a second. I can type df, and yeah, you see there's a nice tabular appearance here. I told you about these slicing methods and so on. I don't need to go through them all. I want to highlight the describe function. So I think this has similar versions in R and Python. So if I type describe df, I get some statistics. So the different variables, these are the different column names. It computes the mean, the minimum value, the median, maximum, number of missing values. And this is somewhat important. So data is dirty often. Data is not tidy. There are missing values in data sets, and we need a way to work with that. We need a way to handle missing values. This data frame could be inefficient to work with because the element types of these particular columns here are a union of missing and float 64. And you remember that Julia really wants to know types in order to be able to generate really fast machine code. So if you have these union types here, it's a union of both missing and float. We want to get rid of that. And in order to do that, we can do drop missing. Just show you this way first. If I do drop missing df, it will return a new data frame with the missing rows removed. But we want to do it in place. We want to modify the data frame in place so that it gets updated. And that's why we use an exclamation mark. I didn't talk about this, I think, before, but the convention in Julia is to use exclamation mark at the end of function names if it's a mutating function, if it mutates, if it changes the input arguments. And if I do this now, there will be a new data frame. So df will now have 333 rows instead of 344. Yeah. Okay, that was it. Let's just talk a little bit more about the data. So what are these different columns here? Build length, build depth, flipper length, so on. These are measurements. I think it's real data. It's measurements on penguins on a few different islands. And let's start plotting. First, just a general overview. We will be using plots.jl. That was probably the first library, but and it's one sort of the basic one. It's powerful, but there are many other options. So people coming from R might like the Gadfly package. There's Vega Lite, Makey, and so on. Statsplots builds on top of plots, but has more statistical types of plotting, like, I don't know, density graphs and so on. We will use statplots and then later on statsplots too. So hopefully this was already added in the exercise previously to our new environment. You don't have to type along now. I just want to show you how relatively straightforward it is to work with plots. This will take a little bit of time. Plots is a big package. So what does this gr function do? It sets the backend to gr. There are many options. We can have a look at the documentation for plots. You can plot using different plotting backends. There's a matplotlib backend for those coming from matplotlib. We can define x and y to be something and then just plot. And what's nice about VS Code is that this will appear now in a new window in a second. I guess it's pre-compiling now. So this is the time to first plot problem. So if the first plot will take time, all following plots in the same REPL session are fast. Yeah, so here's the plot. We can move it like this if you want, you know, have it side by side and so on. I just wanted to draw your attention to this as well. There are, again, mutating functions, exclamation mark, X label and Y label. This will now operate on the same plot, mutate the same plot. Here now the X label is there. If I type it here, it gets a Y label too. So that's a nice interactive way to work with graphics. I can even add a new curve, add a new variable, plot exclamation mark now, because I'm mutating the same plot. I get a new curve. Two final things. One can save plots using the save fig function. And I'll just show you how you can compose, combine many plots into one. So we can define P1, P2, P3, P4, a plot, a scatter plot, another plot, a histogram, and to plot them all together with a particular layout. So 2 rows, 2 columns, you just call plot in this way. So I'll show you what that results in. I'll just close this plot for a second. P1, P2, P3, P4, and then combine them all. Yeah, so it automatically looks rather good. Anyway, let's apply this now. This is where you start typing along. Let's apply this to the Penguin dataset. If you haven't already done so, import plots and set the plotting backend to GR. I will just tidy up my script in the meantime. So let's do a scatter plot. Okay. These are all the observations and plotting build length, build depth. Maybe what do I want to do? I want to modify markers and colors. This is how you would do that. So I'm just adding, there are many, many different options, of course, to these plotting functions. Change their appearance. Something is wrong. Not sure what I did wrong. Oh, some typo. Yeah, this is just to change the appearance. And one can change the theme to a dark theme. So maybe I wasn't sufficiently clear about this before. So what I'm doing here is to press Shift Enter on any line of code that I want to execute. I hope that didn't cause you any confusion. So I've set the theme to dark now, executed this line, execute this line, it becomes a little bit dark. Finally, let's group the observations. So this is like group by with pandas data frames. I can do it already here in the scatter plot. I will group the observations by species. There were 3 species of penguins, and they should have different markers. So I choose 3 different ones, different colors. So where do you find out about marker shapes and colors? It's here. There are links: list of named colors, list of marker types, list of themes. So let me just copy paste this. Tidy up a bit. Shift Enter. Okay. So clearly there is some difference between these 3 penguin species, right? They are clustered around different centers of mass here. I wanted to show you one last thing. We can use stats plots. So stats plots has more statistical types of plots, like the density plot here. And you need to call it a little bit differently. You need to use this if you want to plot a data frame directly. This stats plots package exports a df macro. And so this is how you call functions, plotting functions in stats plots with a data frame. You do @df, name of the data frame. And then instead of passing the data frame with particular columns, you just give the column symbols here. So if I would do this, okay, it looks something like this. I just wanted to give you a very brief introduction to plotting. There's lots you can do. There are many different packages, which there's not one main package that rules them all or so. Like it's somewhat different, maybe to different with some Python or R. People select a plotting package based on preferences, based on use cases. It's not all of you work with machine learning. I just wanted to give you a flavor of what's possible in Julia. You can, maybe I'll just start because I'll tell you that there are these traditional machine learning packages. There's a port of scikit-learn directly. I'm not sure if it's feature complete or has feature parity with Python version. I'm not sure, but the native Julia package, I think, for traditional machine learning is MLJ. It has many algorithms implemented and many different convenience functions for working with data. Deep learning, I think there are some options there too, but Flux is the main package. It's very rapidly, it's actively developed, and it's a full-fledged deep learning package, batteries included. Compared, I think, to TensorFlow or PyTorch or so, it has fewer explicit API calls for features like deep learning features like regularization, embeddings, and so on. But it's easily extendable. It's pure Julia. I think practitioners of machine learning using Flux, they often look into the source code. They can extend the source code and so on. And it's composable like many other packages in Julia. So you can work with images, differential equation solvers, data frames, and so on. So the final part of today is to just walk through a machine learning workflow. So the idea is that we have this data, we have the penguin data set. We want to learn to classify penguins based on these observations. If you just measure the beak length, the flipper length, the weight, whatever, the machine learning model will tell you which species of penguins this is. So what do we need? We need a collection of data points for the objective function that the machine learning model will optimize. We need to define the objective function, or also called cost or loss function. We need to define the model, and we need to define an optimizer. And then we do training using those definitions. So I don't need, I already have my data frame. I just need to import these two packages here, Flux and MLJ. And there are exercises at the end. Let me just tidy up the spacing. Using Flux, using MLJ. Probably takes a while because it's going to pre-compile a big package. To select the data that we want to use, this is just selecting from the data frame all the columns that are not the species, because that's the target that we want to predict, not the gender of the penguins and not which island, but all the physical measurements of their beaks and whatnot. And the targets will be the species column. We then use this partition function. Again, this is not the only way to do machine learning. There are probably many other ways. But for convenience, there's this partition function as part of the MLJ package, which partitions the data into a test and a training and a test set. We specify that 80% should be in the training set, 20% in the test set. We shuffle the observations because the data frame is ordered to get a more random selection. We can select a random number. And multi is simply because we do it with both X and Y here. So Flux is compiled. Let me just copy paste. Yeah, I'll walk you through the rest. If when running on GPUs, you would want to convert to floating 30 single precision, 32-bit floating point numbers. And then we convert the data frame here to an array and transpose it. This is pre-processing. Machine learning always comes with a lot of pre-processing. We then, instead of the observations Y here, we use this one-hot encoding. If you come from machine learning, you know what this means. If not, then it's simply a way to represent categories. So because we cannot work with strings, addly again to chinstrap, but we can work with booleans, ones and zeros. And then this is to check how many of each class there are to see that the data sets are somewhat balanced. Just copy paste here. Execute these different lines of code. I can mention one thing. If you put a semicolon after a line, it will not print the result of that expression to your REPL. So if you want to, if you don't want this verbosity, you don't want everything printed, you just add a semicolon. So what does this do? It counts the number of species. So we have here in the training set 116 of one type, 9456. So they're relatively balanced enough, hopefully. This thing here is the one-hot matrix. It's something that comes from Flux. It's a type of array. which contains this one hot encoding of the categories. We define a loss function. We use the cross entropy method. Define a convenience function accuracy here, which will be called during the training to show us the accuracy of the model. Enter, shift enter. This is not how you should teach. You should not be shift entering all the time, but never mind. This is how we define a model. This, I think, is similar to PyTorch. I guess you can do the same thing in Keras. We chain together different layers. So one dense layer, dimensionality is the number of features. We specify the number of neurons, which will be 10 here. Another dense, this is the input layer, and then there's an intermediate, this is the buried layer, and then it ends with a softmax. Don't worry about this if you don't do machine learning, it's a machine learning language. Copy paste. Any questions? We define a callback function. So this is a function that we pass to the training function of Flux, which gets called at regular intervals. And as you can see here, if you went through the quick reference guide before the workshop, this is an anonymous function. It has no name. All it does is to show the result of calling this loss function here. One selects an optimizer, Adam, and then extracts the parameters of the model into theta. Enter. I'll just push through the rest here. This is something to check the predictions before we start the training. What xtrain is the data set that we want to train on. You see that the model is initialized with random assignments. So what this will result in the end. So this is when we call the model that we defined here. We call it on a portion of the input data, just 5 columns. And it's a random, so it's you see the same numbers in each column. It's predicting that every single penguin is roughly this middle category here. While the truth is actually that here we have this penguin and the same and a different one and so on. So the accuracy will be very low. I guess this is just the random prediction, 33%. So let's see now if the model will actually learn something. We call the train function, passing the loss, the parameters, the data set, optimizer, the callback function, and we run it for 10 epochs. It will run, and it should print the accuracy to the REPL here because we passed this callback function. And then we can test the accuracy after training. This will actually be fast once it runs the first time. We can run 100 more epochs and it'll be quite fast. In the meantime, let me just check HackMB. It's still running. I just want to tell you what happens roughly. What happens is that the training will not be good. It'll be terrible, hardly any improvement. And that's why is that? It's simply because there is some problem with our model. And there's an exercise below. At the very bottom, there are exercises. One is to play around with plotting in Julia. Another one is to actually improve this deep learning model. And the improvement is to add this batch normalization layer to normalize the features. The features have large range. So the measurements of the penguins, they the numerical value, absolute value of them can range from something like 15 to 6,000, and this can result in very bad training. So this is the standard solution from machine learning. You add a batch normalization layer, and then you actually use, instead of this sigmoid activation function, you use ReLU. So let's see if it's already trained. Yeah, it's trained. I can run 100 epochs. Now it was fast. Accuracy is only slightly better, right? Only slightly better. I can plot the results. So predicted species. Then I do the opposite of one hot encoding. I use one cold encoding and pass here the predictions on the test set. So this is the test set. And to go from this one hot encoding with just ones and zeros or booleans, you want to get back the categories here, add the ligand to chain strap, do it like this. And then it's the true species. This is the prediction. This is truth. And then we plot or generate a nice confusion matrix to see the results. Confusion matrix came from the MLJ package, if you remember. Okay, it's worthless. So predicted species here is predicting all the penguins to be Adelie. Ground truth is not the same. So your task in the exercise is to improve it. There is a solution, but I will leave that to you. You can do it now. I don't have to leave right away. You can stay around if you want. Otherwise, you can do this in the afternoon. But that concludes today from my part. So yes, we are in the section writing performant Julia code. And I'm introducing a toy code, small scientific application solving the heat equation in 2 dimensions. This is the project TOML file. This is the main module file. Specifies uses the module keyword here, imports the packages it needs, includes the source files, these 3, and exports a struct and a few functions. The setup creates this field custom type, which has a few 2 integers, 2 floating point numbers, and an array. And this is a parametric type you see here. T is a subtype of abstract array. This means that we can pass in any array type, which is, well, basically any array type, because all array types are a subtype of abstract array. I didn't talk about this yesterday, but this is an outer constructor. So you can have inner constructors and you can have outer constructors, or you don't need any constructors at all. There is the default one. But the point of defining this outer constructor here is that you can define a field type, a new variable of type field, specifying only this nx and ny and the data variables, and then it will automatically give you a new field with some default values of dx and dy here. So this is an example of an outer constructor. Here's a way of extending a method that already exists in the base library. So base is always loaded. Everything is in base, plus, minus, sinus, exponentials, everything is in base, right? All the basic language features. And we can add a method to the deep copy function, for example, accepting a field type. And what happens then? It gives you a new field with the same parameters as the field that you pass in, plus a deep copy of the data field. There's an initialization function which one uses to create a new field type. And then it calls this generate field function here to initialize some very simple. It creates a disk in the middle of the 2D array with a fixed temperature. 5 degrees, and outside the disk it's 65 degrees, and then there are some boundary conditions here along the X and Y edges. Okay, I just want to give you this brief introduction of the code. So there's a visualization function in IO, and then what you will be working on and what we will be focusing on is this core source file with 2 functions, or actually a few functions. The computational workhorse is this evolve function here. It accepts 2 fields, 2 numbers. It's a double loop. It calculates an X derivative, a Y derivative, and then updates the current field, the data of the current time step, with from the previous time step plus X and Y derivatives multiplied by constants here. And then one needs a swap field function here to swap the current and the previous time step. A simple function that calculates the temperature, average temperature, just summing over the data field and normalizing it. And then there's the simulate function, which is called from the outside, accepting 2 fields and the number of time steps, printing some average temperature, defining these constants here, A and dt. dt is the time step. This is, you'll see how this works in practice, is to show a nice progress bar as you're running the simulation, printing stuff to the screen. And then there's a loop over time steps where we call the evolve function in each time step. And then the fields are swapped, and this is something to increment the progress bar. And finally, the final temperature is calculated or printed. There are tests in this repository as well, but I just wanted to give you first and show you the code. So when you're trying to parallelize a code, when you're trying to optimize a code, you always start with benchmarking. And Julia has good features for benchmarking. Base Julia, the base library, already has this time macro, but it has limitations. It only evaluates 1 execution. And if you remember yesterday, we talked about the pre-compilation. So if you call this only once on a function, it's going to be slow the first time because Julia is compiling the function and you will be measuring the compilation time. If you run it again, it'll be much faster. So you could do that, of course, you could run it a few times, but there is this benchmark tools package, which exports new macros for you to use at btime and at benchmark. And this is what we'll use because it gets better statistics and gives a nicer visual output. And just as with these other packages we discussed, test.jl and revise.jl, this should be in your default environment. So let's just do this together. And I will now open up a new, I open up VS Code, and I will open up a new directory. Open. I want to go to Julia, and then I want to, where do I want to go? Workshop. And let's just open up this folder here. I just want to bring up the REPL. I want to close these. This is from my history. Let me resize the window. Okay, I'm back to a new REPL here. Which environment am I in? I'm in the default environment. I entered the package manager. Here, you should do as I do, add benchmark tools. So my Julia session is was doing something here, but they should install in a minute. Well, actually, I already have it. So it won't do much, but there are no changes for me, but for you, it should be installing the package. And if you're using a VS Code session from yesterday and you're already in some environment, the way to get back to the default environment is just to type activate enter. So you remember that you can do activate and then some environment if you want to, or you can do activate dot for the current environment, or if you don't add any arguments, just activate, it activates the default environment. So let's do this now together to start benchmarking the heat equation code. If you have Git, you can clone your repository, clone this repository. If you just copy paste this command, first you should navigate to where you are, where you want to clone it. So I know that not everyone is on the same operating system, and not everyone will have the same terminal. If you don't know how to do this, or you don't have this same environment as I do, maybe you can just download the zip file. This is a direct link and should take you to a download page. You just download it, put it into your Julia folder, Julia/workshop folder, and you unzip it there. Let me just clone it myself. I will jump to a terminal. Clone. Oops. Okay. Jump back to the lesson. I go back to VS Code and open this directory now. So I go to the left sidebar to the file browser. I go into heat equation. Well, I think maybe what I want to do, it's simpler. What I want to do, sorry about that. So file, open folder. I want a new window first. And here I want to open the heat equation folder. Go to Julia, workshop, heat equation. This is what I want to do. Open here. Close this window. I want to create a new script where we try to run heat equation. So let me just create a new file, a text file, not a Jupyter notebook, and I can save it. I pressed Command Shift Command S. You can also find the save under file here. Then let's just call it run benchmarks. JL. There will hopefully be time for you to catch up if this is a bit too fast. Let me just copy paste. Like so. I will open up the REPL. So remember, Control Shift P or Command Shift P brings up this quick search, and I want to start the REPL. And here, what I want to do is to open up the package manager and activate the current heat equation environment, because there is a project.toml file there. And if you remember, there was another command to download the required packages. All the packages that you find in the project.toml file, they're not automatically installed when you just activate the environment. There's another command called instantiate. Yeah, takes a little while. Not too long. Well, I already had some of these packages installed, I guess, in the default environment, so it reuses packages. Now this will hopefully work. I want to import heat equation. And the first time I do this, it starts pre-compiling. First time I run using heat equation, it pre-compiles the package. So now that it actually takes time here because it pre-compiles plots, for example, which is a big package. What's happening in chat? Yeah, so there's a question. Yeah, there is already this example.jl file in the repository. So if you download the zipped folder, the heat equation repository, there is already an example.jl file, and I guess it's the same one as you see here. I just forgot about that. So you can use that one. So that you can use the example.jl file. Pre-compilation is done. I will now import benchmark tools. As fast, I define number of columns, rows, and number of steps. I initialize two fields, the current and the previous field. What just happened? Not sure. Oh, I had the mouse cursor in a funny location. So yeah, now it defined these two fields. We can start by visualizing. This is the function from io.jl. Now it has to pre-compile the GR backend. Okay. And again, VS Code is nice because it gives graphical output in the editor itself. So this is the initial temperature distribution. We can run the simulation. And here's the progress bar that I mentioned. So it shows this, if it takes more time, you see it incrementing gradually. And then after 500 time steps, there will have been some evolution. The borders are a bit fuzzy. So yeah, seems to be doing what it's supposed to. All right, I hope the pre-compilation times allowed you to catch up. This is how the code works. Let's now try the benchmark macro. So we just call simulate again, but we prefix it by benchmark. And what will happen? It actually runs multiple times now, right? It's gathering statistics. So let me know if anything is not working now. Okay, so this is the output. It gives a range, minimum, maximum time. Actually, the range was rather narrow now. Sometimes you see a bigger range because there are other things running on your computer. So there can be a big statistical error bar really on the timings, a median value, and then a memory estimate as well. How many allocations, how much memory was consumed. So that's how you benchmark. The B time macro, will be using that later, is simpler. It just does the timing. Something that's useful to know about is that you can also capture the output of benchmark. you can, I'll just copy paste this. This once. So you capture it. There will be, yeah, it's a particular type here that it returns. And you can access, for example, the times that the benchmark macro recorded through the times variable here. And typically you would maybe want to take the minimum value.
Can you also control the number of times the benchmark will run?
Yes. I don't remember the flag now. So let's have a look at the help. I go to the help menu at benchmark. This is the documentation. Actually, it's, let's see now. It doesn't show us the flags, I'm afraid. There are many setup expressions. You can set the number of iterations or samples to take. I guess you would have to visit the documentation of the benchmark tools package. It should be printed here, but it's not. So where was I here? So you see that it spits out a number. This is the minimum execution time, which is raised to the power 10 times 10 to the power of 9. So it's in nanoseconds. I think, no, it's in microseconds maybe. Anyway, this will become clear. Okay, so that was benchmarking. You can catch up with this later if you're not done during the exercises. I want to tell you about profiling too. So you benchmark when you're optimizing or parallelizing, and then you profile to get further details into what's going on, where time is being spent. And there's an inbuilt profile module, part of the base library, that gives you tools. And there are other packages as well that I'll show you. So it runs sampling at runtime and gathers statistical information about where the time is spent during the execution. And one uses this to identify bottlenecks. So that's always the first step in optimizing. And this is the famous quote from Donald Knuth: "Premature optimization is the root of all evil." It's a bit harsh, but close to the truth. So let's profile heat equation now. I will go further down in this script here using profile. Oh, yeah, it's part of the standard library, so you don't have to add it. You don't need to do this, strictly speaking, the first time, but this is, if you run it multiple times, you need to clear the backtraces from an earlier run. Just grab this whole snippet here, and then you, yeah, so we initialize the fields again, and then you run the profile macro. Get an error. Okay, again, I was just had the mouse cursor somewhere in the middle of the line, and Julia doesn't like that. So now it ran correctly, and I can print the profile. So this is the profiling information. It's very not very friendly, read friendly. But so the numbers you see here are the numbers of samples. So it checks at regular intervals where is the code now, and sometimes you know, some parts it only visits once, but sometimes it visits very often, like in the core source file here, for example. So, but this is a little bit difficult to get an overview from. There are options. You can print at a certain depth and so on. But I just want to show you, I'm not going into any details here. I just want to show you what you can do to get a more graphical more graphical overview. This prof view macro is not part of profile itself. It's added in the Julia extension to VS Code. So hopefully you will have it already installed too. And so it's a part of the VS Code extension. I will run this macro instead. And what happens now is that you, maybe because I'm sharing full screen, I can afford this. This is maybe a little bit easier to browse. So you see here we also have time, total time, self time. I can expand this something inside heat equation, right? One can go on expanding this. Let me move it over here. So it's you can see the depths here. Okay. Still, so obviously it's inside simulate, and there are these two inbuilt functions, set index and get index, which are quite costly. So these are actually inside the evolve function. So this is simply where Julia is in the evolve function setting, updating array elements of the current array. One more thing I wanted to show you here up in the right corner, there's this fire symbol. If you press this one, you get a flame graph where you can see a more graphical overview. Anyway, this is not, I'm not going into any depth here, but it's good for you to know that the profile module exists and the prof view macro to get easier information that is more easily digested. Did it work for you to run this?
Yes.
Okay. Okay, so that's that was what I wanted to show you basically, and then just mention that there are other packages that you would need to install: profile view, profile Vega, stat, profile HTML. Some of this is good for Jupyter notebooks also. pprof, which is wrapper around the Google pprof tool and so on. So if you want a more detailed tool for profiling, there are definitely options. Now I want to discuss a few performance considerations, definitely not an exhaustive list. I will show you a more exhaustive list at the end. I just want to mention that Julia is just like Fortran and also like Matlab and R. Arrays are stored in column major order. So the arrays are stacked one column at a time in memory. And this is different from C, C++, Python, or NumPy. And this is very important. So because it's important to think about memory in this way, because if you have a double loop and you loop over rows instead of columns, in the innermost loop, you will definitely lose performance because you get so-called cache misses. And if we were to swap the two for loops here, so first loop over X and then loop over Y instead of the opposite, it would probably give us something like double the execution time. You can play around with this later. So keep that in mind. Julia is column major ordered. Another very simple way to increase your performance is to add this inbounds macro wherever you are accessing array elements. You could actually put this array macro right in front of the for loop instead, and it would apply to the body of the loop. But because we're actually going to put other things in front here, we're going to parallelize. I moved the macro here in front of each line. And what the inbounds macro does is to tell the compiler that all the memory accesses are, they're not out of bounds. They're all within the bounds of the arrays here. if you use this incorrectly, if you use inbound and then you're indexing beyond your arrays outside of the allocated memory, it will crash or give you incorrect results. But in this case, we can be pretty sure because the looping is such that we're only accessing within the arrays. So we can run this with confidence. And let me go back now to, I want to open up the core source file here. So what time did we get? I want to rerun maybe. Let me just, for clarity, take this away for a moment. Don't remember the time we got. Let's rerun this. And then I will compare it to running it with @inbound. Just add that. And remember, because of the magic of the revise package running in the background, I can just save the source file, core.jl, and my Julia session realizes that something has changed, and it will recompile anything that's needed, and I don't have to restart the REPL here. So what did we get? We got a minimum time of 3.88 seconds. I will now save this file. I run the benchmarking again. Let me just go back to the schedule to see if I'm behind time or what. There we go. Yeah, of course. Well, I think time will still be less of a, I'm hoping there will still be more time for exercises today. And there's quite a good speed up here, 2.3 seconds. Simply by adding this, it's very simple. Okay, so one more thing I wanted to tell you about, static arrays. So if you're working with many, many small arrays, so on the order of 100 elements, it can be better to statically allocate them on the stack rather than on the heap. And so what static arrays are, they are arrays whose size the compiler will know, so it can perform optimizations. I don't have to run this, you can run it yourself. So here's an example. This is a small random array. If you would import static arrays using static arrays, and then you would you can convert an existing array to a static array with this syntax here, it actually provides a huge speed up, so a factor of 3 here. But this will not work with larger arrays, only on the order of 100 elements. So finally, this was just a very brief, superficial overview of what needs to be kept in mind with regards to performance. But there's this very good page, performance tips. I'll mention 2 actually in particular. So this is a long page with many hints and advice, what to do and what not to do. So avoiding global variables is actually very important. So if you have global variables like this, the performance will be greatly degraded, actually. There is a way to circumvent the problem, that if you really want global variables, you can specify a const in front. Const will not mean that the value of the variable cannot change. It simply means that the type is fixed. And that's the information that the compiler needs to know to generate fast code. There was one more thing I wanted to mention from here, I think. Yeah, so everything that is performance critical should always be inside a function. because functions are pre-compiled and specialized and optimized by the compiler. But before you write any serious code in Julia, you should go through the entire list here. Okay, so this is just a short exercise. We don't need to break up into rooms right away. You can just try this yourself, enter the inbounds macro. You can also play around with the static arrays if you want. Let's spend until 9:50 on the exercise. And then after that, we take a 10-minute break until 10 o'clock. All right, so we are now ready to start discussing parallelization, and there will be more work for you to do. So I will share my screen again. So I will now jump to the parallelization section here. But you can see the link here on the left. And oops, I want to collapse the sidebar like so. So we will get an overview of how you can parallelize in Julia, and in particular how to use multi-threading and multiprocessing. So multi-threading on shared memory systems, a single computer, a single node, and multiprocessing for multiple nodes. And there's the shared array package that I'll show you. So before talking about how you can parallelize code, it's good to know that there is actually lots of parallelization going on in the background by default, by automatically. So I could define these two functions, for example, these two arrays, A and B, large random matrices. And I want to set this up by running the htop command. This is like top. It shows me the load on the processors. They're already loaded here 50%. There are 4 physical cores on my machine. I guess they're the number 0, 2, 4, 6. And then there's hyperthreading. But if I now, what do I want to do? I want to multiply the matrices together. A times B, it'll take a while. I go to my terminal, and you see, they're all completely busy now. So this operation, multiplying 2 large matrices, is parallelized by default. I don't need to keep running it. I can just kill this. Anyway, but beyond that, you often need to parallelize yourself manually. And there are many types, or there are a few types of approaches. This we will not cover. So asynchronous tasks and coroutines. You can define tasks and let the runtime decide how to optimally place those tasks during runtime. This is not really HPC. It's not parallelization. It's just about suspending and resuming computations for I/O, handling events, and stuff like that. So we're not going into that here, but we'll talk about multi-threading, where you can use more than one core, but it needs to be shared memory, only on single computers. And this is in the threads standard library. It's already shipped with Julia in the base library, and one imports it directly. And then there's distributed computing. And what this actually does is to run multiple Julia processes, independent processes with separate memory spaces on, it could be the same computer still, but you can run it on a cluster, or you can even run it on all the servers in your lab if you have the SSH accesses to those machines. We will talk about stuff in the distributed module. There are things like MPI. We will not go through it because it's not an MPI workshop. But if you know MPI, if you like MPI, you can write MPI code in Julia too. There's the MPI.jl package. GPU computing we talk about next. So threading, let me just copy paste. I will go to my here again. Threads.endthreads 1. I have one thread, just like you. So the way in which we use multiple threads, we need to start Julia explicitly with more than one thread, with a -t flag, and set the number of threads, or we can use the auto keyword here, which automatically runs on all the cores. One can also use an environment variable. But there's also a way to set this inside VS Code. So if I go here to the extensions, and I go to Julia and the little settings button here, and then I go to extension settings, and then I make it like this. So I can now search for, these are all the settings for the Julia extension. There are many, many settings, and this might be something you would like to look into later, because you can customize how VS Code works. But I will look for threads, and I can set this to 4 or 2. Let me not set it to anything right now. We'll just keep it at 1. And what if you do this, if you update this number, you will actually need to restart the REPL here, so that you have all the threads in your REPL. Okay, so how do we use this? The main approach is very simple. From the threads library, just use the @threads macro. And what this does is to parallelize a for loop to run with multiple threads. Actually, let me set the number to 4. This does not take effect immediately. I will need to quit and restart the REPL. I now have 4 threads. So if I run this piece of code, what does it do? It creates a new vector with zeros, and then it assigns the elements to the thread ID. Let me just paste it right here. So you see that there was a loop over 1 to 10, and the different threads grabbed different parts of the loop. So thread 1 took the first 3, thread 2 took the next 3, thread 3 took the second 2, and thread 4 took the last 2. Let's see if we can gain any speed for something that is maybe a little bit more costly. Well, let me go to the run benchmark script, and I'll just copy paste this function. It's a function that takes the square root of an array. And then let's have a look at the threaded one. So the difference is small. The only difference is that we decorate the loop with a @threads macro. So, and it has a new function name, threaded square root array. Functions. And how do we call it? We can create a big matrix, 1000 times 1000, and then we run these two. So now you will play around with this later. It's inconvenient, of course, to have to set this in the VS Code extension setting every time we restart. So we'll do it in a different way. I haven't imported benchmark tools. Autocomplete. This is the serial version, and I'm using the btime macro just to report timing, not the full benchmark result. This took roughly 2 milliseconds. The threaded version takes half the time or so. So clearly it doesn't scale perfectly. I have 4 threads, but the timing was, it took half the time. But there are pitfalls. If you're familiar with shared array programming in other languages like OpenMP or so, there's always the risk of so-called race conditions. This is where the order in which threads read from and write to memory can change as a result of change the result of a computation. Because the threads are independent, they will be accessing array elements and writing to memory. And sometimes many algorithms are not thread safe. So one has to work around that problem. This was thread safe, these functions, because each thread can independently do its work without stepping on other threads' toes. So here's an example of a thread unsafe function. The serial version, what does this do? It accepts an array. It creates a new array S. No, it just creates a number, a 0, of the same type as the elements of the array A. L type is just the element type of A. And then it loops over the array here, and it sums up the square roots of the elements. So I'll copy paste the serial version first and shift enter to define it. And let's take this now, this naive implementation, if you will. You see the difference? I've just inserted the threads macro. I will evaluate that too. And then let's call it. Did I have an array? Yeah, I had a 1000 by 1000 matrix. I can do square root sum of A. It gives me 666,000. I can do the threaded square root. No, threaded square root sum, I think. Is that the name of the function? Threaded square root sum. It gives the wrong number, right? Yeah. It gives 179,000. And that's because of the race condition. So you see that we're summing up the square roots of the array elements, and the threads will be accessing memory and writing to this S variable at the same time. And this will give the wrong result. You can avoid this problem by using atomic operations. So this is how you would do it. You would use an atomic add instead of the regular plus equals to operator. And you would have to define this atomic type of array here. But if you try this, you'll see that it's extremely slow. Atomic operations are slow. I can just run, let's just do the time macro once. Let's run it twice. I timed the serial version. It was 3 milliseconds. I do time on the threaded square root sum with atomic operation. It gives the right result, you see. It gives the right number. Let's run it again to get a more reliable timing, but it's much slower. It's, 30 times slower. That's another thing to keep in mind, that you can get these floating point issues, that some computations depend on the order in which they are performed. And I guess if you just add numbers of different size, that can affect the order can affect the result in a small way, but still. So the workaround to not have to deal with atomic operations because they're slow is to refactor this code somehow. And here's one way to do it. This is a workaround. We sum up the array, the square roots of the array elements partially. So each thread, so this is a new vector with zeros and number of threads. The dimension is the number of threads. So each thread will be summing up its own portion of the matrix, and putting it into an independent index of this partial vector here. So you need to refactor the code. And then when you've done this, this is parallelized. After that, you can sum up all the individual results from the threads here into your S variable. And this will be both fast and correct. Function. Run it a few times. It's 3 milliseconds. Actually, it's not much faster than the original one. What did I get here? 3 milliseconds. It's a little bit faster, but this clearly does not provide a big speed up because the mathematics here is simple. Okay, I just wanted to emphasize this. You can use threads for an easy parallelization, but you have to watch out for this race condition problem. I'm just wondering if am I missing the threads in front? I'll redefine the function. Oh, didn't matter. Anyway, so there's another package called floops, which is a superset of the threads inbuilt package, and it supports different types of reductions and so on. And it's on a higher level. So if you're interested in shared memory parallelization, you should look into the floops library here. You would have to install it. Okay, distributed computing. I will go through this maybe semi-quickly so that you have more time for exercises. So it's the distributed module. One needs to install it. It's a somewhat different approach to frameworks like MPI, in the sense that the communication is one-sided. So there is a master process that controls the work on worker processes. It's not that every process is equal as in MPI. And the way to run multiprocessing is to start Julia with Julia minus P4, for example, or Julia minus P auto, I think, to take. Now, well, probably that doesn't work. You specify the number of processes. But you don't need to restart the REPL as we saw here with the threads. Instead, what you can do, fortunately, is to dynamically add and remove processes. So let's just maybe in the REPL import distributed, and then we can do nprox. I have one process. What I want to do, I can add processes. I can check the number of workers and so on. So if I add a proc, add 2 processes. It added 2 processes with particular IDs, 2 and 3. I can now repeat nprox. I have 3 processes, out of which one is the master one. If I do n workers, I will see 2 because I created 2 worker processes. And I can get the IDs of the workers with workers. The IDs are 2 and 3. I can also remove processes. I think you can do it like this, 2 and 3. Remove processes 2 and 3, and let's check the workers again. Yeah, there's only one, it's the master process, and prox 1. So there's a question about whether distributed works for Slurm clusters. Yes, I will come back in a second to that question. Okay, you can manually manage your processes this way. So on a cluster, you would use something like the cluster managers package. I think that's the recommended one. It has it can work with Slurm and other what do you call it? The schedulers on a cluster. But maybe in contrast to MPI and other in C++ or Fortran, you need to specify machine files. So a machine file will be a file with the IP addresses or something of the compute nodes. And they can be generated automatically if you're running a job on a cluster. And they need to be accessible via passwordless SSH. Okay, so this is one way to manually work with processes. You can spawn jobs on them. So there's this comes from the distributed package. There's the spawn macro and the spawn at macro. Spawn will randomly or automatically assign a job to one of the workers. If you do spawn at, you specifically ask it to be run on a particular process. So if I do add prox 3 again. So this statement here spawns, it runs my ID, which is just a function that makes a process print its own ID, and it also creates a random number on the process that we specify. So you see, actually, it's a bit funny that the processes are now called 4, 5, 6, because 2 and 3 were taken from earlier. So this will not work. I would have to put it on process 4. And what does it return? So R is a future object. It doesn't have its result yet. In order to fetch it from the process, from process 2, we need to use the fetch command here. So my ID was 4, and this is the random number that was executed on the created on the process. This is one way to work with the distributed package. There are more higher level constructs available too, like the distributed macro for for loops. And this can also be used with reductions. So you can reduce with sum or any other operator. And the pmap function. So if you're familiar with map, you can map an array, for example, to a function. If you use pmap, this will be distributed over many processes. So let's have a look at the square root sum function that we had above. We need to refactor it a little bit to work with these distributed and pmap higher level parallelization options. So we refactor it a bit to accept a range R. It accepts the array and a range, and then it loops over the range. And you see that we decorate the function with at everywhere. This comes from distributed. This is something. This is to let load or define the function on all the processes. Here. I think maybe I'll let you experiment with this yourself. I will just show you what the idea is. So the at distributed macro with a plus, for example, how would we do that? So we create first, we take the array and divide the length of it by 10. Actually, this now assumes a 1D vector. So let's do A is equal to random 10,000. It's a vector. And divide the length of it by 10 so that we can split up the work. And what does this do? So for R in, and this is an array comprehension, if I just copy paste this here, you see that it's a vector of ranges. So between 1 and 1000 with a stride of 1, 1001 to 2000, 2001 to 3000, and so on. So R will be picked from this list of ranges, and this will be executed then with an individual range in every loop. So that's how that works. PMAP, it's similar, except it accepts, PMAP is here. It accepts a function. So this is an anonymous function. So you take the square root sum range function, and then second argument will be this list of ranges here. I hope that makes sense to you. And then at the end, we need a sum operator here, because the PMAP function will, let's just run this. Where are we here? Got some problem. Invalid index, type float. Yeah, I think that's probably the problem, yes. Cast it to an integer. Yep, that was it. Thank you. So if I run it without the sum in front, so each process will be computing its own part of the array here. And then the sum is in front to just sum the contributions. Finally, this could be done with the spawn at macro, but it takes much more code, right? You have to figure out how you want to split the work between the processes manually. All right, so a few more words. So a very common use case of PMAP is to use it with inbuilt functions or other functions that you've defined. So here is just an example. There's the linear algebra package, which is part of the standard library. And you want to do singular value decomposition for a bunch of matrices, for example, random 100 by 100 matrices. You can easily pass a function from another library into the PMAP function here. So that's just to so that's just to inform you about that use case, because PMAP works best with relatively heavy calculations. One final thing, and there will be an exercise on this: shared arrays. They're also part of base Julia, and they define, so the new shared arrays type, it's a subtype of abstract type, and the difference to a regular array is that it's shared across multiple processes on the same machine. So you can still you can use the multiprocessing methods like PMAP and distributed, but it will still be on the same machine because the shared array is shared. The memory will still need to be in one place. And here's just one way how you could do this. Square root array is the same function as before. This is the serial version. The shared array version would be, you could have the same function name, right? Just define a new method where you specifically indicate that it accepts shared arrays. And then you can use this construct here. So first you actually need to prefix with this synchronize macro here to wait for the result of each process, but you distribute the loop. So I just mentioned that there is another package called distributed arrays, which is useful for some type of work. It could in principle be useful for the heat equation package, but it's a little difficult to use. It doesn't have any high level constructs. You have to construct these D arrays, the distributed arrays, where different processes that could be living on different computers, different nodes of a cluster, own a particular set, a particular subset of the array. They have read access to the full array, but write access only to a portion of the array. And then you can distribute work that way. But it's there's a lot of indexing to manually take care of. So it becomes a little bit verbose. So I will not go into it here, but if it sounds interesting for some problem of yours, you can look into the distributed arrays package. MPI, again, I will not go into it, but it works as you would expect, mpi.jl. And that concludes my overview. So any questions in HackMD? Regarding Julia Hub, can we see the specs of the machine clusters? So I will tell you now, actually, because it's good actually that you, I think, log into Julia Hub already, those of you who will be using Julia Hub. I was asked by the support person, I was asked to ask you to log in 10 minutes before we start using it. So maybe at the end of this exercise session and before the break, you can log into Julia Hub and possibly even request, yeah, you should request the machine. And I want to add that here. We actually will get V100s. Okay, I will add documentation about this to the HackMD. So before the break, after the exercises, please start up, log in and start up an instance on Julia Hub. I will write down some instructions here. And here's a good link. It seems a look at communication intensive performance in Julia. Thank you. But okay, I will introduce you to the exercises. Multi-threading heat equation. Focus on the evolve function and insert the threads macro. Unless you write using threads, you will need to specify the full, you will need to resolve the name. So threads.addThreads. Put it in the right location and benchmark the effects with, measure the effects with benchmark. And I mentioned it's rather annoying to have to change this setting here in VS Code every time. What's better is that you have a script. You can use the script that we started on and run the benchmark, capture the result, and then just print the minimum of the times so that you can run it then from a terminal, or I hope you're able to run it from a terminal somehow. And you would call the script with Julia --project or --project equal to point. That means that you will use the project TOML file from the current directory. And then you can specify the number of threads with -t, and then the name of your script. And you can try increasing the size of the problem, lowering the number of steps so it doesn't take forever, maybe 20 steps, and see if it scales better. And there is a solution. Using shared arrays. Here you maybe, I think it's easier if you write, extract this function, put this function in your script that we're working on, the benchmarking script, or create a new one, and just work on the function iteratively. So try to create a new function for shared arrays. You have to import distributed shared arrays and the benchmark tools package. And then, work on this function here. And then you can benchmark it, for example, like this. There are instructions. You can use dynamically the add procs function to add processes, and rm procs if you want to compare with, if you want to go back to fewer processes. And finally, there's an exercise on parallel mapping. So the heat equation code is not very useful for a PMAP construct, but take this function instead. It's a function that estimates pi with maybe a very inefficient method. It creates random numbers and checks if this sum of their square is below 1, and then computes an estimate of pi that way. So write a parallel version of estimate pi. There are some hints here. And that's it. Yes. So if everyone does this, I'll give it a couple of minutes for you to do these steps if you haven't done them already, and let me know how it goes. So here on the instructions, I will show you. So this is how it should look after you log in. On the right, you see applications. Don't select Pluto, select Julia IDE, VS Code. And then you should press a launch button, which is here. And then you get a menu. I cannot reproduce it here because I already started my session, but you get a box or a menu where you can select what type of instance you want. And you should select a GPU instance. And then change from K80 to V100 flavor of GPUs. So V100 NVIDIA GPUs. And then 2 hours, specify 2 hours. Anyway, so GPU programming. This is surprisingly easy to do in Julia. So there are different high-level and low-level methods for GPU programming in Julia. Particularly, we'll talk about Q arrays. Again, a subtype of abstract array. That's for the high-level interface. GPU kernels for the low-level interface. So as you might have heard, there is now competition on the HPC accelerator market. So NVIDIA used to dominate completely. Every cluster that had GPUs had NVIDIA GPUs, but now increasingly AMD is entering the field. So the large Lumi supercomputer in Finland has AMD GPUs, and so will Dardel at the KTH in Stockholm. And then Intel they're working on it too. I don't know if there are big machines planned in the US with Intel GPUs, but they're still somewhat behind NVIDIA and AMD. So we will talk about CUDA.jl because we have no access to NVIDIA GPUs, but there is AMD GPU.jl, which is very similar. I mean, the syntax is practically the same as CUDA. It's just instead of Q array, it's a ROCM array and so on, but you can easily translate between the two. Hopefully this will be the same for OneAPI.jl, but this one is still far behind the other two packages here. So to install CUDA, you do something like this. This you will not have to do on Julia Hub. I just want to mention that you can get access to GPUs for free on Google Colab if you have a Google account. They don't offer Julia per default. I mean, you get a Python environment, you get a Python notebook, but it is possible to install Julia manually. And there is some helpful person here on the internet who created a Colab notebook with everything prepared for setting up Julia and using GPUs. I've tried it though, and I don't know what has changed. It's not working perfectly, but you can play around with it yourself later for a free, trying out GPU programming with Julia on Google Colab. But so far I haven't been able to make it work. Just a few words. This is not a GPU programming workshop. I just want to draw your attention here, if you haven't seen this type of graphic before, that GPUs are quite different from CPUs. Instead of a handful of cores, they have thousands of cores arranged into these streaming multiprocessors. So you really need to program differently. You need to have large amounts of data that you can split up and that you can perform concurrent calculations on. So that's really where you draw the benefit from using GPUs. So let's just dig right in. So I will move my Julia Hub instance here. This is VS Code, which is nice. We don't have to change completely the user interface. What I did when I started up VS Code was to click a new file. You see, I have some stuff here, which you probably don't. It's from earlier. You can click a new file here, and you can rename. You can name it something, GPU.jl, and then the first expression is using CUDA. So using the GPU directly can be as simple as this. So we can define a new array. We use _d as a convention for things that live on the device. And then just declare it to be a Q array. And we can put a regular array here. This is a vector. And it automatically becomes, it gets transferred to the GPU. One user interface difference here on Julia Hub compared to VS Code is that Shift Enter runs everything. It runs the whole notebook. For some reason, I don't know why it's different. So if you want to run an individual line, it's Alt key Enter. And you see that the first time I run this, it actually needs to download, I think, GPU drivers and so on. Takes a little while. So if you're doing work on the GPU and then you want to take it back to the CPU for some post-processing or for printing or for writing to disk or something, you can just use this syntax here. Just make it a regular array again. And then you can work with the array A on the CPU. So this will be extremely slow. You don't want to work with small data structures on a GPU. But let's say we have something bigger, big matrices, 2 to the power of 13 in dimensions, and we want to run a matrix multiply. Using benchmark tools, oops, probably not defined. You will have to, okay, it's still working. Okay, so now everything is installed for me. I want to execute this cell. So I'm pressing Alt Enter now to run line by line. You see this array here, AD, is now living on the GPU because it's a Q array. Let's time this one and time this one. I will maybe resize the window a little bit so it's not at the very bottom. There should be a dramatic speed up. I will check it back in a minute. Another common use case is to use vendor libraries, so NVIDIA libraries, for common operations, matrix multiplications, QBLAS, fast Fourier transforms, QFFT, linear solvers, QSolver. All of these kernels are wrapped in CUDA.jl, and you can simply use them with Q arrays. So here's, for example, how you would do a matrix multiplication, multiplying A and A together into B. Yeah, so many things just work, using some solver here, QR factorization, solve an equation with backslash operator. This is supported in regular CPU computing, but if you do it with Q arrays, if A and B are Q arrays, this will run on the GPU. You can run QFFT like this. This is no different from what is possible in other languages. What's maybe particularly cool about Julia is that you can use higher order abstractions built into Julia for data living on the GPU. So things like broadcast, map, reduce, accumulate. As long as your array is living on the GPU, these things will just work. So this, as an example, let's revisit this square root sum function here that we had in an earlier part. Let's see the timing. This is the timing from the two matrix multiplications. So on the CPU, it took 8.7 seconds. On the GPU, it took 28 microseconds. So it can really, yeah, you've heard maybe if the GPUs are fast, and here's proof. So square root sum, this is the same one we saw before. How could we use these higher level constructs to port this to the GPU? So we first need to take the square root of array elements, and then we sum the result. And we use these constructs here. We can simply compose the problem by adding together a map where each element of A is taken, the square root is taken, and then we call reduce with a plus. So maybe we should use a bigger, do we have A? A is a big random matrix. I will just copy paste this here. Now it actually asked me for permission to paste. So I paste, yeah. So this is pretty cool. It's a one-liner to run a kernel on the GPU, but we actually didn't need any low-level programming. We could use these higher-level constructs here. Writing your own kernels. This is, many algorithms aren't amenable to higher-level programming, unfortunately. So in many cases, for more complex algorithms, you would need to drop down a level to writing your own kernels. And if you're going to, yeah, so it's useful to know how to do that. Typically, this is done, so far, CUDA is the main language for this. You write kernels in CUDA. Things will look similar in CUDA.jl and Julia, but with many simplifications and still in a higher level language. So let's see how that works now. So let's take a very simple vector addition function. In reality, it doesn't make sense to write a kernel for it because this you could use a higher level construct for. But just to illustrate the point, we work with a simple function here, add two vectors A and B into a new vector C. So this is how it could look on the CPU. Actually, you could do this in one line even, but we pretend that this is a more complex function and see how it works. I will just show you, I'll just don't have to run everything myself. I'll just show you how it works. We define these things here and we call the function. We could already run this on the GPU using this CUDA macro by converting the arrays to Q arrays and prefixing the function call with @CUDA. This would run on the GPU, but it would be bad because every single GPU thread would be doing the same thing. And there's no, the work is not being split up between the threads. So you need to start thinking about the architecture of GPUs and how they are structured. So there are these these descriptors or these parameters. This is familiar to you who have written CUDA before. So the processing elements are split. They're sort of structured according in blocks and in threads. There's a thread ID, there's a block ID, and there's a block dimension. So a simple way to split up the work between the threads on a GPU is to take advantage of these inbuilt variables here from CUDA.jl, thread index .x. We're looping over, this is a one-dimensional array here. These are one-dimensional, so we only need the x component. So that's an index and then a stride. So because we want the first part of the array to be split up over the first elements, processing elements, and the next part of the array to be computed on the following processing elements and so on. And this is one way to achieve it. So we have a for loop. So each thread entering this function will get a unique index and a stride. And then you make the for loop in this way. You loop from the index to the total length of the array with a particular stride. And then when you call the function, when you launch the kernel on the GPU, you can set the number of threads here. But this does not still utilize the GPU fully. There are even better ways to do it. So this would, I think, only run on one of the streaming multiprocessors. There's a more efficient way. Now you see there is no for loop. We just define an index I, which has this typical formula. So this is what you see in all CUDA codes all over the place. This is a way for a given GPU thread entering the function to get a new index in the array. And it'll be, so it's a way to sort of map the arrays over blocks and threads on the entire GPU. And this formula here can just be copy pasted. It's always the same. And then instead of having a for loop, we just check that the index I is smaller than or equal to the total length of the array coming in, and compute the sum. And then we want to launch the kernel. We now have to specify the number of blocks. Maybe I should do this. I'll copy paste it here. And I want to copy paste this too. So the CLD function divides the length of the array by 256 and takes the smallest integer, which is larger than or equal to the division. This is just to make sure that we have enough threads to cover the entire array. I can show you the result of it in a minute. So we set the threads, we set manually to 256 here. Still evaluating something. Execute this. So the length of A is large. It's a large array. If you divide it by 256 and take the larger, we round it upwards, rounded to the nearest integer larger than the result, we get 262,000. And this is how we launch it now. We specify the thread should be 256 and this number of blocks here. Okay, I guess it's doing something in the background. Okay, so there are exercises soon. I just want to briefly go through the rest. We have been using 256 threads, but this might not be optimal. So the more threads we have, the better. The better will be the performance. But the maximum number of threads that we can use depends both on the GPU that we have, which model, and also on the nature of the kernel itself. There is a way to optimize this choice. One can create the kernel first without launching it. So we say kernel equal to @CUDA, but we don't launch it. Launch equal to false, and then the function itself. And then we extract, this is called the occupancy API. We extract the launch configuration of the kernel, and then from there obtain the best number of threads. It should be a minimum of the length of A and the threads that we get here. And then same formula for deciding the number of blocks. This is the smallest integer larger than or equal to length a divided by threads, and then we launch the kernel. So here we create the kernel, but we don't launch it yet. Here we actually launch it with additional arguments, number of threads and number of blocks. So profiling is possible, not in the regular way that we saw before. You can use the NVProf profiler from NVIDIA, if you have it installed, of course. One would specify a keyword, an option that you should not profile from start, because we don't want to profile pre-compilation and stuff like that. And then launch Julia like that. And then when you profile a particular function, you use this CUDA.profile macro. And then when you exit the REPL, the profiler will process and print the information for all the executed kernels. Just jump back here. Yeah. So this kernel got executed. It's just, it doesn't print anything. I just want to also mention that it's straightforward, just like it is with many of the other machine learning libraries in Python. It has inbuilt GPU. So Flux has inbuilt GPU support. So to run training on a GPU, you just load Flux. And given that you have a GPU available, you just need to sort of pipe your training data, your test data, everything that you need on the GPU. You pipe it into a function, GPU. So this gets copied to the GPU. The GPU also needs to know about your model. So you pipe the model into the GPU function, and then you just run training as normal, and it will be running on the GPU. Okay, so enough talking. So any status update again? Any problems? I want to leave the rest of the time of this workshop. It's not a lot. Hopefully, yeah, it's 10 minutes to 12, but feel free to stay longer to work on this. And you think you should be able to utilize the full 2 hours on the GPU on Julia Hub. So you can play around as you want. And there's an exercise. So take the same evolve function, just copy paste it here to a Julia script. This is the vanilla one, accepting abstract arrays, and write a kernel, because this is not, we cannot make it work easily, I think, with any of the higher level tools, higher level constructs, but try to write a kernel. And I hope the steps that are given here will be good enough for you to figure out a way to port this kernel port this function to the GPU. So there are hints. It needs to return nothing. This is some internal GPU thing. You have to add a return nothing. And the arrays now, the cur data and the prev data arrays, they're 2-dimensional. So you need both the X and Y dimensions of the threads and blocks to map the arrays to the hardware, to the threads on the GPU. And then you should specify tuples for the threads and tuples for the blocks when you launch the kernel with @CUDA. If you want to debug, if you want to print the number of print the thread ID of all the threads entering the kernel, one can actually use this qprintln function. But this is very slow. You should not do it to measure timing, for example. If one gets warnings or errors relating to types, one can, similarly to what we saw yesterday, there's the code warn type macro to show us any possible problems with types in the function. And there's a corresponding device code warn type for GPUs. And then it's good to check the correctness, that it's computing as it should. One can compare the CPU version and the GPU version roughly like this. So run this once on the CPU, run the corresponding thing once on the GPU, because the arrays A1 and A1D will be updated, and we can check that they're approximately similar here. And then you can perform some benchmarking. There's another exercise without a solution on porting the neural network we looked at yesterday, if you're interested in that. But of course, feel free to play around with any of the other stuff from here. So you have the GPU for a couple of hours, do what you want. But maybe, and I was thinking we could split up into fewer breakout rooms because they became a bit load imbalanced. We can have 2 breakout rooms for some teamwork discussions. And of course, if you need to leave at 12, you should do that. And I'm just happy you came. But this will be the final part of the workshop. We split up into breakout rooms for 20 minutes until 12:15. And then we drop back and have a final discussion. If you need to go, there is a final episode with an outlook, where to go from here. There are some useful links, depending on what you're might be interested in. A pointer to the discourse platform for Julia, where you can ask any questions. It's a friendly, nice environment there. Heads up for the JuliaCon workshop that takes place annually. It's free. And for the first time, the SciMLCon workshop will be organized in spring and also free.